Yeah, so I'm going to be talking about satellite observations of the Earth's atmosphere, improving our ability to predict weather. And on the screen, we have tropical cyclone imagery. And I'll be talking about a spectrum of very tiny satellites. So on the left, we have a mission that I'm leading for NASA called TROPICS, which is flying a constellation of satellites about the size of a carton of milk. They have scanning radiometers. Those satellites took these images on the screen. And we'll be talking about larger aperture systems that are still flying on small satellites. We have much larger, 5 orders of magnitude type larger apertures than a 3D CubeSat for sensing the atmosphere. So I'll give you a little bit of the story on the technology development needed to enable those observations and how we've been able to do that. All right. Let's see here. So to advance the slide, can I go? That's the best way to use this thing. Click the mouse.
Click on the up arrow.
Okay. So for future reference, I just click the arrow and click the mouse, I guess.
You can use the clicker right now, I think.
Okay. This guy. All right. Should I do a test run?
Yeah, it was.
Thanks.
It doesn't work. Yeah, go to the presentation.
Okay, all right. Beautiful. Okay. Thank you very much. All right, so just for some background, I wanted to give a little bit of broad context on how we currently make measurements of the atmosphere and how those inform the forecast, right? We take out our iPhone and click on the weather app and look at the forecast. These forecasts come from all these measurements that are driving numerical weather prediction models, generating forecasts. And there's a lot of data sources that feed the forecasts, right? Here's some of the predominant ones. So first and foremost, and relevant to my talk, are the satellites. We have geostationary satellites. This figure is not to scale. So the geosatellites fly 36,000 kilometers above the Earth. They're staring down at the Earth. They have very high persistence, but the spatial resolution isn't that great because they're flying so far away from the Earth. The polar orbiting satellites fly much lower, so they get better spatial resolution because they're closer to the Earth. But it takes 12 hours for the satellite to, the Earth to spin underneath the satellite and the satellite to revisit the same point on the ground. So the persistence isn't as good. And there's a host of other things that we use to inform the weather forecast. GPS, we get radio occultation data from GPS, aircraft sensors, weather balloons, drop signs, radar, buoys, ships. So all this stuff feeds into the global observing network that runs the forecast system. All right, here we go, the moment of truth. Yes. All right. So if you kind of rack and stack the value of all those measurements that they provide to the forecast, you get a chart that looks something like this. So what I'm showing you here is the benefit, like the impact on the forecast of all those measurements. So we have microwave sounders, weather balloon radiosondes, geostationary wind measurements, all kinds of aircraft data buoys. And the point I wanted to make, which motivates what I'm going to talk about, is the thing at the top here is this microwave sounder. The advanced technology microwave sounder is the largest driver. The biggest benefit to the forecast comes from these microwave sounders. So I'll talk about why that is and the work we've done to try to fly better versions of microwave sounders to improve our forecasting. Okay, and I'm going to talk about tropical cyclones specifically, because TROPICS is a tropical cyclone mission. So a very specific kind of forecasting that we're trying to improve. And tropical cyclones are very, very important. They're very impactful. We're trying to figure out, where is the tropical cyclone going to go? How is it going to intensify? How can we improve our emergency management and so forth? So the tropical cyclones form in this relatively narrow latitude bands. due to how the moisture and the heat circulate in the atmosphere and the ocean. And the hurricane structure, so I'm showing here in the lower right, we need to measure some observables that are sensitive to how the hurricane derives its energy from the warm, moist air, how it intensifies, and I'll talk about how we can measure that from the satellite. So it's a very interesting problem, a lot of dynamic activity for cyclones, and it's fully understood now from a satellite perspective because we can't measure those effectively with our current satellites because of persistence and resolution. Okay, and there's certainly a lot of tropical cyclones. We're getting more of them, and the intensity is growing. So this is just one example showing, there's 9 simultaneous tropical cyclones, either named storms or forming storms at one time. The frequency of occurrence is rising as we're going into time. So it's a really challenging problem due to each of these events are dynamic, hard to measure, and we're getting more of them and becoming more intense. So this is one of many examples of this is Hurricane Irma. And so the plot on the left here shows that the forecast had it going on the right side of Florida, and what actually happened, it went on the left side of Florida. The forecast got that wrong. This has implications for warning people. People will pay less attention to the warnings if they're wrong. So we really have to do a better job of getting that forecast right. And the way we do that is making the measurements of the hurricane better. That's really what we're trying to do with systems like TROPICS. Okay, so if you look at what you need to measure for a tropical cyclone to inform the forecast, there's really 3 key things. Okay, the first key thing is the profile of humidity, right? The vertical profile. How much moisture is there in the storm environment as a function of altitude and kind of XY space around the hurricanes. That's really the engine that forms the tropical cyclones. That warm, moist air gets drawn in, kind of vertically advective, and that drives the storm. So we need to measure humidity. We need to measure temperature in the storm environment and also in the eye of the tropical cyclone. It turns out that what we call this warm core anomaly, that red warming in the eye of the storm aloft at about 8 kilometers, is very highly correlated to the intensity of the storm. So if we can measure that from space and track that over time, that's a very good marker of intensification. So temperature is important. And then the third thing you can probably imagine is precipitation. We need to understand how hard is it raining around the storm? What's the structure of the precipitation, the spiral rain bands, asymmetries in the storm? All those kinds of things are important to understand what it's doing and how it might intensify. So we need a collection of temperature, humidity, precipitation at very high resolution in 4 dimensions. That's kind of the problem statement, right? So we need to design an observatory that makes those measurements with high spatial resolution, high temporal resolution, and high sensitivity. And we don't really have that today. We've got the polar orbit that has the good spatial. The geostationary can't measure down into the storm to get the physics in the center of the storm. So that's really what we're trying to get at with TROPICS, to bridge that gap between a geosensor and a low orbit polar orbiting sensor. Okay, so there are a number of ways, as I mentioned earlier, that we can try to measure tropical cyclones. Ground-based radar is fantastic, but we don't have these in the open ocean, right? There's very limited satellites that can provide radar data of a tropical cyclone. Those are very sparse. Aircraft are again sparse. The geostationary sounders that I mentioned earlier, so the reason that those aren't very effective is we can't fly microwave sensors on geostationary because the antenna sizes would be huge to get effective data. So we've only got visible IR, and that doesn't penetrate the cloud tops. So microwave sounding, passive microwave radiometry, is a really nice compromise because it can penetrate into the storm center, get the thermodynamics, the temperature, the moisture that we need. It's got useful spatial resolution. It's not as good as the infrared, but it's good enough to resolve the eye and the warm core. And we can, as I'll show, miniaturize the sensors and fly them into constellations. So it's a really good kind of compromise measurement to get everything we need for tropical cyclone study. Okay, so as you probably know, today we fly microwave sounders. So NOAA operates a system of polar orbiting satellites. These are really big, expensive. They barely fit in this room, and we don't have very many of them, right? So the regret is that the polar orbitals fly over a storm. We've got to wait 4 to 6 hours for the next satellite to fly over. And And a lot can happen in 4 to 6 hours for an intensifying hurricane. So we're missing all that dynamic activity in the hurricane with the current system of polar satellites. So the idea is, can we take the microwave sounder, make it smaller, fly it on a smaller, more portable package, and fit it on a CubeSat, like we saw earlier today, the CubeSat lab. Make them, instead of $1 billion a satellite, can we go to $1 million a satellite and fly a lot of them, right? Then we can drive down make the resolution better. And there's a lot of other advantages to proliferating a constellation of very small affordable satellites. So this is really the motivation of a constellation like TROPICS. Who tries a sensor and then fly a lot of them? Okay. So just a few words on how we make these measurements of temperature and moisture and how we derive a vertical profile. So part of the magic of atmospheric sounding is that we use these absorption lines. So what I'm showing you here on the right is the atmospheric absorption near a line due to oxygen at 118.75 gigahertz, right? So there's a very strong line. And as you move away from the line in frequency, the opacity of the atmosphere decreases, right? It becomes more transparent. So if we put channels along the line at various opacities, from a satellite, we can sense down to different depths of the atmosphere. So that's how we get the vertical profile. By tuning the frequency off the line, we can sense at various altitudes, and that gives us the vertical profile. Okay, so on the technology side, we've been working for over a decade to try to miniaturize the sensor. Remember the satellite I showed you earlier was, fits in this room, and the instrument is about the size of this desk, right? So we asked the question, what would it take to make that smaller? And the laws of physics dictate that you need the antenna size to resolve the eye of the hurricane. It turns out that aperture is about the size, maybe 10 centimeters. It's not that big. Most of the instrument is electronics, which we can miniaturize. So over the course of the last decade or so, we've been working to make the receivers smaller, the electronics smaller, and figure out how to accommodate that on a very small, affordable CubeSat. So that involves making the receivers very low power, small, sensitive, stable. So we've been working with our colleagues at UMass Amherst to do that. We figured out how to accommodate that payload on a very tiny CubeSat bus. So we have the payload is rotating once every 2 seconds as we fly along to scan across the Earth to generate the image. So that introduces challenges on how you control the satellite, how you geolocate the beams, how you keep everything stable as all that motion is going on. So we figured that out. We made the first prototype back in 2015 and flew that. There's an animation there at the bottom of the payload spinning on the end of the satellite. So that was successful. We got some NASA funding to build a multi-band radiometer. So the Micromass 1 was a temperature-only instrument. Murata was temperature, humidity, and precipitations. Those are the 3 variables that we need for the tropical cyclone. That was a few years later. Then we launched Micromass 2A in 2018. So Murata did not scan. So Micromass 2A was the first CubeSat that had the scanning radiometer and the 3 variables that we needed: temperature, moisture, precipitation. So that was really the existence proof that this was possible, right? So we flew Micromass 2A in 2018. The first time anybody has done this and showed that it would work. So there was Micromass 2A data on the left, that's 94 gigahertz. There's the big expensive satellite on the right, ATMS, and the data is comparable. So we knew we had something when we proved this out, and then the race was on to try to make a constellation of these. Okay, so kind of fast forwarding to where we are now. So Micromass 2A in 2018, that was the first ever CubeSat microwave sounder with a scanning payload. We were selected to do TROPICS. TROPICS was a NASA mission I'll talk about here in a minute in detail. So there was the TROPICS Pathfinder satellite we launched first in 2021. That was the first CubeSat to image the globe, provide those measurements on a global basis. We launched the constellation back in 2023, so I'll show a lot of data for that. So this is really the first constellation demonstration. And then more recently, we've seen some activity. So we actually did a technology transfer of the TROPICS technology to a company, Tomorrow.io, who is now launching their own network of satellites based on TROPICS technology. They've got, I think, 4 satellites on orbit now and have 18 on orbit next year. The Europeans are launching small satellites for weather. And the next part of this, and this is actually the second part of my talk, is a larger satellite. So the regret with TROPICS, as I'll get into later in the talk, is we're using millimeter wave channels. So the lowest frequency channel on TROPICS is 90 gigahertz. And that's not really great for penetrating into the storm for precipitation. So I can apply lower frequencies down to 23 gigahertz. So CREWSR does two things for you. It's a very large deployable planar aperture, and it enables electronic scanning. Right? So the beam doesn't need to mechanically move. We can point the beam anywhere in the field of regard as we fly over. That enables all kinds of interesting things. So that'll be the second part of my talk. So let me talk about TROPICS, and then I'll get to CREWSR. And by the way, as I'm going through this, feel free to shout out questions or raise your hand or whatever. Don't feel like you have to wait till the end. Okay. All right, so let me talk about TROPICS. So this is a NASA Science Mission Directorate mission. So this is not a tech demo. This is a full-up NASA flight science mission selected back in 2016 as part of the Earth Venture portfolio. The idea here is to develop a fleet of these very small CubeSats, 3 new CubeSats, 5 kilogram class satellites, and make very high quality measurements of tropical cyclones. There's an example in the bottom there. So this has a pretty large team behind it. There's a science team from NASA, NOAA, a bunch of universities, Wisconsin, MIT, behind this mission. We have a project scientist from NASA Goddard. There's a picture of the payload here in the lower right, showing kind of the engineering heroics that were needed to cram all that electronics and receiver technology into a very tiny 10 centimeter cube with a scanning motor at the bottom and a slip ring to get the data back to the bus, which is working really well. So I'll show you some of the details of this mission and how this is actually working. Okay, so this slide is intending to motivate, again, why we need this kind of capability. So here are some infrared images at the top of the screen, right? And we're just seeing the cloud tops, right? We're missing all of the thermodynamic structure in the storm. And the current LEO satellites, we only get a couple of shots of the tropical cyclone, right? So we're missing all the data. So here's TROPICS, right? So if I overlay the TROPICS constellation, we're getting much more rapid revisits of the cyclone, and we can see the evolution of the eye and the rain bands. This is the information that we need to try to improve the forecasting of the storm. So that's what we're trying to do. Okay, so we are leveraging a lot of the new commercial space capabilities to pull off the TROPICS mission. So we launched on a Rocket Lab Electron launch vehicle, which is relatively new. We're using commercial ground stations, KSAT and Atlas, to get the data down from the satellites. Blue Canyon Technologies made our CubeSat bus and operates the CubeSats for us. We're in a very specific orbital configuration, so we're inclined at 33 degrees. And the reason for that is to put the satellites right over the latitude belts where you saw the cyclones forming in that early chart I showed. They're forming about 20 degrees latitude north and south, right? So that's exactly where we put the satellites. We can fly over them very frequently. And then the data are moved around to MIT, Wisconsin, and out to the general public through the Goddard archive. So that's how it works. And one interesting thing is that with this commercial ground network, we're able to not only take the data very frequently, we can get the data out to the forecasters very quickly. So the latency of the data is about an hour, which is really good, better than what we're doing now by quite a bit. Okay, so we launched the Pathfinder satellite in 2021. That was our qualification unit. So we launched that one to try to check out all the facets of the mission. We then launched the 4 constellation vehicle. So TROPICS-1 is the Pathfinder that has since deorbited 18 months ago or so. We had a launch failure. Our first launch of the constellation vehicles of 2 vehicles failed actually. So we were all bummed out about that, but the next 2 launches worked fine with Rocket Lab. So we got 4 constellation satellites launched. One of them has since been inactive. We have 3 working now. So we're getting a median revisit rate with these satellites of about 70 to 90 minutes. So that's still much better than the 4 to 6 hours they were having to deal with the non-operational satellites. So a big step forward in performance. there's some details on the chart about the altitude. So these are flying at an altitude of about 530 kilometers. And they're working really well as we speak today. Okay, so a little bit of detail on what these satellites are and how they work. And they're really an engineering marvel, I think, how small these things are and all the capability that we have been able to put in these things. So the array, the solar array, is moving as the satellite is orbiting to track the sun to get the power to the spacecraft systems and the payload. The payload is turning, the bus is rolling to keep the array on the sun. So there's all this motion on this little satellite. So there are reaction wheels inside, counteract that, keep the satellite stable, point at the ground. We need to know where we're pointing. So there are 2 star trackers on board the satellite, so we can geolocate the data. We have a very wide swath. So we scan out to about 2,000 kilometers on the swath to get a very wide field of regard. And we've got a 12-channel radiometer making very sensitive measurements of the temperature, the moisture, the precipitation structure of the storm, and beaming that down to the Earth on this S-band radio. So a lot going on in that very tiny satellite package. The spatial resolution, so the size of the footprint on the ground, is roughly 20 kilometers. So that's not as good as a geostationary visible imager with sub-kilometer resolution, but that's good enough to let us resolve the eye of the hurricane and measure that 1 part anomaly. So it's a really nice observatory for measuring the temperature and the moisture environment of the tropical cyclone. Okay, so here are some details on the payload, and I want to refer back to the chart that I showed you on that oxygen absorption line. So remember I showed you that we're sampling channels along the skirt of that absorption line. So that's channels 2 through 8 for the channels that are going off that oxygen line for temperature sounding. That gives us the vertical profile of temperature. We've got a channel at 90 and 205 to give us imagery. So those images that I showed you earlier were all taken at 205 gigahertz. That's the first time we've ever flown a channel at 205. And I'll show you a slide coming up that shows you why that's important. Then we have 3 channels near 183 gigahertz to do water vapor profiling. So that gives us the amount of moisture near the storm. Here's some details again on the spatial resolution of the channels and the sensitivity. So these are pretty close to state-of-the-art values for these parameters. Okay, so here is an animation. Do we have any latitude to make it dimmer in here, to turn the lights down? You can see that? I very much. Right. So what I'm showing you here is an animation. So this is essentially all the Pathfinder data, the entire mission sped up. And what I wanted to show is just to give you an idea of the quality of this data. You can see the wisping of the water vapor as the data flies by here. You can see hurricanes. If you look really carefully, you can see one spinning up and moving down here. You can see the forming of the Atlantic Basin. So there's really amazing data coming out of these very tiny satellites as they orbit. So this is really amazing to see this.
We have a question.
Yeah, sure, yes.
Oh, so it looks like those little black diamonds or rhombuses or whatever, are those seem to be coverage gaps.
Yes.
So once in a while, they'll flash up, they'll grow in size momentarily.
Yep.
So those pulses where you have increased coverage gaps, are you able to correlate those to any particular type of anomaly?
Okay, so that's an excellent question. So one reason that there are gaps is our ground station, they turn out to be in Australia, South Africa, Dubai. When we fly over a ground station, sometimes the data is invalid. We have to maneuver the spacecraft to dump the data. So that messes us up for just a small amount of time. So that's one reason of the gap. The other reason of the gap is just the swath isn't quite long enough to cover the equator, right? But we have pretty much nearly global coverage for this. It's pretty close, except for those 2 things. Is that where you're going with that question?
Yes, I think so. I think also I just have haunting memories of solar flares, and I saw one big, what looks like a momentary outage.
Yeah. So we do have outages due to solar flares, but those are very rare. I mean, we've got about 99% data availability on that, which is another kind of amazing fact about these CubeSats, right? We don't have the money to afford what they call S-class space qualified parts all the time, right? We're flying parts that you would buy off DigiKey or even, Walgreens, what's the pharmacy here, or CVS, an SD card. These things have SD card memory, right? The way you design for that, two things that you do. One is, if you take a radiation hit, you reboot, right? You just turn the satellite on and off again. That gives a lot of redundancy, resiliency. And then we have multiple SD cards. We've got the constellation, right? So we've got kind of a resilience due to numbers. So we do go offline sometimes. We just reboot and it's recovered. So it's amazing how far you can get with those COTS parts. Okay, so here is a slide that I like to show. So on the left is the big satellite with ATMS, an amazingly good instrument, right? So this is their most transparent water vapor channel. This is Kong Ray from last year, a nice image. And here's our image with I had to make our satellite enlarged by a factor of 50 just so you could see it on the screen. It's like 1 pixel. It's so tiny. And there's our image, right? So that is pretty good, right? I invite you to select your favorite image of those two, right? So this is our new 205 gigahertz channel. This was the largest warm core. Remember that spot that I showed you, the red warming of the eye, we've ever seen with any cross-stack sounder ever was with ours on the storm with our channel. So it's got amazingly good structural imagery data from TROPICS. And we're getting this, every hour. So this is really amazing data that we get with this. Okay. All right. So how does that help us? At the end of the day, what we're trying to show is that when we assimilate the TROPICS data, we get a better forecast of the tropical cyclone. And there are really two things that we look at there. One is the track forecast, and one is the intensity forecast. So we have a science team that is off doing all kinds of experiments on that. These are two examples, one from NASA Goddard, the Global Modeling and Simulation Office, has shown that when we start to assimilate TROPICS data, we get a much better track forecast. So the one on the image on the left, the black is kind of the truth. And as we add in the TROPICS data on the right, the forecast, the blue and the green, converge to the black. So we get a much better track forecast with the TROPICS data added. Here's another example from investigators at the University of Utah, showing that as we add the TROPICS data in, we go from the blue to the red, right? We're spot on to the truth. Right? So there's a lot of information that's showing us that this data is very valuable for forecasting. So we're doing a lot of these trials now to quantify all this. Just to give you a sense for the data products that we generate from the science team for TROPICS, there's all kinds of things. So there are the native radiances, which I've been showing you, those images of the storm. We generate temperature and moisture profiles, precipitation, rain rate, intensity estimates, all kinds of things that you can download if you want to off the web right now. So there's a whole team behind the generation of these products, generate the products to validate them and get them out to the general public. Okay, just a couple of examples. So again, we have 12 channels on the TROPICS payload. They each do a little different thing, from 90 gigahertz all the way down to 205. So these are global images, just to point out that for the constellation vehicles, we only get to about 40 degrees latitude north and south. So we don't have the whole globe. These are where the tropical cyclones form. And it's really nice data. The data is good enough for climate studies. It's very stable, very well-behaved instrument. So those are images. So one thing we look at very carefully is the calibration of the sensor. How stable is it? And how large are the departures from our models? And the answer to that is it's very good and very stable. So this is over a couple of years of the mission, almost no slope at all to the calibration. So that's very promising. This is against a model, GS5. And these are departures from a model. And they're the Gaussians are relatively tight and they're kind of well-behaved, nice Gaussian shapes there. So this is exactly the kind of thing you want to see, that your model is able to predict what the satellite is measuring. And here are the kind of the comparisons, right? So it's very well behaved with respect to what the model thinks the answer should be, and the satellites are responding very closely to that. So that's very good on the calibration. So let me give you an example of an intensity estimation. So here is an example of Hurricane Beryl, and I'm showing you successive shots. These are again at 205 gigahertz. As I flash through these, you can see the storm changing, swirling. The eye is getting more pronounced. And when it's really intensifying, it's got very, this small pinhole eye. And what we can do is measure the temperature inside the eye and derive that warm core anomaly and relate that to intensity. So here's what happens when we do that. So this is a slice through Hurricane Barrel. So on the left, I'm showing you the temperature anomaly. So the red is warming relative to this pixel outside the storm, and the moisture anomaly. So we can relate these to intensity. And when we do that, we get a very accurate estimate of tropical cyclone intensity. So the Wisconsin group is doing this. So again, the truth is the black, and the tropic estimate is the gray squares. Essentially nail that. So it's very accurate estimate of intensity for that temperature anomaly technique. Okay. One interesting thing about the TROPICS mission, this is a science research mission. It's intended to better understand the science behind tropical cyclones, but we have been able to get this data into the hands of the operational community, which is somewhat unusual for a NASA science mission. This is not in our basic charter to do this. But the data has been so good that NOAA and the Navy and others have funded us to get the data down with very low latency so they can use it operationally. So the Hurricane Center, Joint Typhoon Warning Center regularly uses TROPICS data to inform their analysis and their reports out. So we're very proud of that. It's been very valuable for them to understand the structure of the storm, where the eye is, how big the eye is, and those kinds of things. It's another good shot of Conray. Okay, so that's the kind of the end of the TROPICS part. Any questions on that or anything that you'd like to ask before I move in? Yes.
You mentioned that all the data was on SD cards.
Yes.
Was there any sort of like radiation protection on them, or were they just?
So that's a great question. So yes. So well, the only thing that we did with the SD cards was we essentially ordered every different manufacturer's cards. We radiation tested them. We saw kind of how they perform in a radiation environment. We picked the best one. And even that is not foolproof because, we picked, Samsung chips, right? But even Samsung has got 10 different foundries that they use for making the chips. So you don't know which foundry they use for whatever. You can't track that parts. So we did some pre-launch testing and picked the best one that we thought we could use. But there's nothing special about how we use them or any protection we have on board. Just kind of rolled with it. And so the good news, one reason we're able to be a little cavalier with the SD card is that we're flying over the ground station so frequently, the requirement on our memory is pretty low. We don't need much memory. We can actually use the memory on the flight computer, which is much more robust. So I'll tell you that right now we flew 10 memory cards. One of them is working right now. Right, so we're hanging on by a thread, but it doesn't matter because we can download the data as frequently enough. Yes. Yes.
Questions about the gaps when you are scanning the Earth.
Right.
So how do you actually plan to do any post-processing or anything to actually cover the gaps?
There's not much we can do there. We just don't have measurements there. So, you can ask that maybe you can interpolate across the gaps. That gets you a little bit, but there's really no data there. So not much you can do.
That seemed like those positions are almost constant over the time.
They are. Those are very constant, predictable. So, one thing that you might be able to do, and this kind of ties into what I'm about to talk about, is if you knew where a storm was, you could maneuver the satellite a little bit in advance to move the swath edge over to catch it if you knew that. We didn't try to do that because that requires a lot of planning. Yeah. But in principle, you could do something like that to try to make that a little bit better, but we didn't. Yes.
Yeah, so we know signals that was originally designed for these tropical storms, but that has been used for we are collecting the data over lands too.
Right.
So for any the tropics, the data that is showed, it has also data over the land. So is there any work going on to utilize the data that is over land? That because we only showed the storms and the measurements.
Yes, absolutely. Excellent question. So one of the interesting things that we learned with the Pathfinder, which has a sun synchronous orbit, right? So we go over the poles with the Pathfinder, is that 205 gigahertz channel is really sensitive to snow, right? So there's all kinds of work going on to see if we can use that channel to detect snow better. And the Europeans, I showed that AWS Arctic Weather Sat, they've got a 229 gigahertz channel. So they're very interested to see how we do with the 205, right? So there's that kind of stuff. But absolutely, yeah. Anything else? Okay, time check. Am I doing okay on time?
Yes.
Okay. All right, so I'm going to talk about another class of sensor. This is CREWSR. So there are really two new innovations with CREWSR. One is, can we make the antenna larger so we can have better spatial resolution and use lower frequencies so we can penetrate the storm more effectively? We want to have a better aperture while still maintaining the affordability of a very small satellite, not a CubeSat, but in the case this is what's called an ESPA class small satellite, so you can still kind of hold it in your hands. And SpaceX will launch ESPA class satellites for about $1 million, so it's not many millions of dollars. It's still $1 million, so it's affordable. So number one is a bigger aperture, better spatial resolution, lower frequencies. Number two is this is a planar array that enables an electrically scanned beam. So we're not mechanically turning on a reflector anymore. That's huge because now back to your point, if I know there's a tropical cyclone here, as I fly by, I can really focus my energy there, right? And I buy a lot in sensitivity, I can dwell on it, I can dither, there's all kinds of things. So that opens up all kinds of possibilities. So with CREWSR, we're trying to prove that's workable, right? So this is what NASA would call low TRL, technology readiness level. But we're showing that we can do this with 3 independent beams. We're going down to 23 gigahertz with this, 23, 31, and 50 to 58. So this is really a game changer from the point of view of resolution and configurability, how we can use the sensor to make better measurements and operate in a smarter way. Okay, so this is a NASA-funded effort. So what I wanted to point out with this is, I think that a cool figure of merit to look at here is the ratio of how big the aperture is to how much the sensor weighs, right? So this is a very thin, lightweight panel that we can deploy. And I'm plotting here the sensors that we've flown in the past. ATMS is a sensor we just talked about. There's TROPICS. And the 4 sensors in the middle are very big, 2-meter scanning reflectors that, these sensors weigh many hundreds of kilograms. These are very big billion-dollar class sensors. And CREWSR is 2 orders of magnitude better than those sensors from the standpoint of aperture per mass. It's just a huge leap forward. And it's green because we can electronically scan, right? So we're not beholden to this deterministic static scan pattern. We can look when we want to look. And that's very exciting. And the enablers, the reason that we can do that, well, we're essentially drafting off the communication sector, Starlink, right? Elon Musk, that's amazing technology, right? Those are phased arrays that are flying around, steering the beam. We're doing the same thing here, but at much higher frequencies, right? So we're using these RF integrated circuits to make that possible. Very large format arrays. I'll show you the challenges of that, but there are, many hundreds of thousands of elements on these arrays, right? So there's a huge technology challenge of making that work. There are new technologies for deploying the array. So we got multiple panels that got to snap into place and lock and be very flat and rigid. We can do that now. And there are ways that we can ensure that those panels are flat. They stay flat when they undergo all kinds of thermal deformation going in and out of sun eclipse. And we can talk to the satellites but with very low latency, up and down, right? So we can command them, we can tip and cue, we can say there's a storm coming up next orbit, get ready to go over there. So this opens up all kinds of very interesting ways that you can use this new capability. Okay, so here are some examples. So just a few things that you could do with a configurable sensor that's not the same resolution at the same time. Just very obvious, if you're looking for, and this is an atmospheric river, right? So there's a very dynamic spatial information that we know is there when we fly over. We can configure the sensor to use its best resolving power in the areas of the scene that would benefit the most, right? You zoom in when there's something interesting to look at. So that's the spatial part of that. Same thing with the spectral configurability. We can change where the sensor is looking. It's how far off the line you are based on the phenomenology that you're trying to measure. It's another thing you can do. There's also a geometric configurability. It turns out to be if I fly over the same column of air at different angles, I can use tomography to make my vertical resolution better. So I can do that with this kind of sensor. So there's all these configurability things that I can exploit with these types of sensors. So the question is, how can I build this? So there's all kinds of challenges to making the sensor. So the way this works, it's a very flat panel, okay? So this is a reflector array, all right? So there's a feed in front of this. And then the reflector array has got two sides. There's the side that has antenna patches, radiating side, and the back side is RF integrated circuits. So they're essentially a bunch of phase shifters that introduce a pattern on the array. I'll show you a picture of this coming up. And that allows the array looks to the incoming EM wave like a parabolic dish, right? Puts a phase shift on that. It can steer the beam, shape the beam, and that's how that works. So there are all kinds of challenges to make that work effectively. So that, like I said, there are hundreds of thousands of these RFICs and antenna patches on the front. So there are thermal challenges, mechanical challenges, electrical challenges. So I wanted to kind of take you through the story of how that is working. So the CREWSR instrument is 2 meters by 2 meters. Remember, TROPICS is like this. CREWSR is 10 of these tables, right? So it's much bigger. So it's made of these modular panels. And let me show you how this is going to work. Okay. So a few more details. I think we have some antenna guys in the room here, so maybe this will resonate with you. No pun intended. All right. So each one of these. So this is 5 millimeters on the side, right? Very tiny unit cells. And in each one of these cells, there are 4 antennas at 58 gigahertz, 1 at 23, and 1 at 31. And each one of those patches on the other side of the array is connected to an RFIC that introduces a phase shift. So there are hundreds of thousands of these antennas on one side and RFICs on the other side. So here is how this is. If you look through the array, these are all the stacks of how the thing is put together. I'll get into that in more detail later. Here's a close-up of the feed horns and one of the panels that we've tested in the antenna range. I'll get to that coming up. But you can see how this is all put together. Okay, so that was the radiating side of the reflector array. On the back side are these RFICs. Okay, so they're phase shifters for the 23.8 band, the 31.4 band, and the 50 to 58. So here's the 50 to 58. So what's going on here is it's a 4-bit phase shifter. Okay, so what's happening is there is a series of switches that basically switch in transmission lines of different lengths that introduces a phase shift. Okay, so we can shift each one of these cells with 4-bit resolution over 0 to 360 degrees. And that is important because we can do this. All right, so this is kind of an animation of the phase shifters turning on and off. You can see the contour of the beam moving around. This is how we steer the beam, right? So all those phase shifters together, to the EM wave coming at it, it looks like it's a parabolic reflector that's moving around. It's a planar array. So that's how that works. Okay, so the engineering behind making that panel is extremely difficult in a number of dimensions. So one thing, just the sheer attachment of those integrated circuits to the panel is really challenging. There's so many solder joints, right? So the solder joints have got to be electrically effective. They've got to be mechanically secure. They've got to be thermally effective. So the way that we do that is we have essentially a grid mesh with what we call interposers, where we can mount the RFICs to the mesh and have it all flat and stable. The heat is dissipated out through the panel. We've done X-ray testing to convince ourselves that we can actually solder. Each one of these RFICs has got 36 pins on it. When you multiply that by hundreds of thousands, that's a lot of solder joints, right? So we've X-rayed all this. We don't need all of these unit cells to work for the array to work. We've got a yield of about 99%. So this is all working great. So here's just a little bit of insight into how the panel is stacked together. So again, we're trying to keep the panel flat. We're trying to deal with thermal effects, trying to deal with radiation effects. So these are a couple of things that help us do that. So we've got various materials of stack up, heat spreaders, epoxies, to keep everything attached and flat. So this very careful analysis and planning has gone into kind of choosing how we architect that panel, the materials that we choose, how we bond things together, and that's worked out really well. There's a challenge of controlling, 100,000 chips on the back of this. We've got a network of of SPI bus controllers. You guys know SPI? Yeah. So there's essentially a bank. Again, this is on the back side of the board. There's essentially a bank of a lot of FPGAs with SPI buses fanned out to all those chips, right? So we can control that. And this talks back to the main flight computer. So that's how that works. And then, so the proof is in the pudding. So we've got a panel built and into the antenna chamber at MIT Lincoln Lab, made measurements, and it worked fantastically well. So this is credit to the antenna guys. So, you know, the way you look at this is we have this simulated measurement, and in this case in black, and the actual observations in red, and they are nailed. And this is really close together. Here's the model and observed simulation. So this is fantastic performance for one panel. So now we're building the entire big panel now, but this is really encouraging. This is going to work great. Okay. So in terms of the performance parameters for this, there are a couple of things that we look at. One is the beam efficiency. This is extremely important for microwave radiometry. We have side lobes, and those side lobes essentially contribute to contamination of the observation. If I'm looking at the eye of the hurricane, I don't want to be contaminated by something that's going on way outside of the field of view. So this is a very high quality, narrow, clean beam. So that's very good. We're trying to prove that we can make a large scale panel, which we can. Power consumption. Okay. So some of you may have the question, why don't you put a phased array on a satellite? Right? This is not a phased array. And the reason it's not a phased array is if I have 100,000 amplifiers, that's many kilowatts of power. I can't do that. So the nice thing about the reflector array is I eliminate the amplifiers. I change that into a switch, which I can do with 1 milliwatt, not 30 milliwatts. And I get the power level down to about 50 watts, not 3 kilowatts. Now, the penalty that I pay for that is here. The phase shifters are lossy. Okay. So I've got to deal with that loss in the panel, and that hurts me in two ways. The sensitivity of my measurement is not as good, and I have to calibrate out the effect of the panel. Okay. Now, there's good news on that. The good news is with the array, I'm always viewing the Earth. With a scanning system, I scan across the Earth, and most of my time is off the Earth. Right, so I'm wasting that time. I'm not doing that here, so I can buy that back with this. And for the calibration, I mentioned in a slide earlier, metrology. We have very sophisticated ways to measure, understand the thermal profile of the panel and correct for that. So we can do that. So we have, so the panel will be complete this year, and we're going to fly this on a high altitude balloon. This is why I was asking about the balloons earlier today, to prove that we can solve this calibration problem. We actually fly it. We think we can, but we need to demonstrate that. Okay, so another interesting, we're shifting gears a little bit here at the end. And you might be wondering, how do you test such a system on the ground? Right? How can you convince yourself that with all this configurability, you actually can realize a benefit? And how can you quantify the benefit? I mean, at the end of the day, what's the mission utility of this new sensor? So we've got a relatively new NASA program that we call VIDEO, where we're trying to build in a laboratory environment an ability to test the sensor. And the cool thing about this is the calibration target that we're using is a laser-driven projector. So what's going on here is we have a metamaterial, we heard about that in the last talk, absorber, a high emissivity surface that's thermally excited on this backside by a laser. It's actually 4 lasers that are projecting on that. So we can actually put a spatially resolvable scene on this radiometric scene generator and measure that with CREWSR. And then all the things that have to happen behind CREWSR, we have NVIDIA Jetson processors running on the sensor. It's calibrating the data, estimating features, identifying features, reconfiguring, and then we can ask the question, how well does that work in practice in a test as you fly environment in the lab, right? So this is happening now. So later this year, we'll have a full panel built. Our collaborators at Colorado State are building the radiometric scene generator. We'll have a system test. We'll have a balloon flight, hopefully. So this is all kind of coming together to show how well this will work. Okay. So another cool part of this is kind of the processing that's involved that you need to enable this, right? So you need the sensor in principle can recognize a feature in the scene and reconfigure itself to make a better measurement of what's flying over. So one example of that is a hurricane. So if you fly over a hurricane, you can recognize that there is, a rain band or a warm core, reconfigure the sensor to take a better measurement of that, and see how well you do. So there's all kinds of hardware on board that makes that happen. The feature identification, the reconfiguration of the sensor, and the analysis. So we've got some hardware that we're running to do that. And I think this is actually, I may have seen this exact board in one of your labs today. I don't know.
So you're saying this, just to clarify, so the sensor intelligently reconfigures itself?
That's right. Yes. So it recognizes a feature of the image. There might be a warm core over here. I'm going to go interrogate the warm core, measure it with a better, higher dwell time, better signal to noise, and see if that works better. That kind of thing.
So to follow up on that, so is it using some type of optimization strategy based on sort of a cost function or something?
It absolutely is, right? So there's actually AI. There's a neural network running on board the processor, right? So the algorithms that we're delivering for TROPICS are all AI based. They run like this. So we can actually, it's very well suited for that. So we're running that algorithm on board the sensor, identifying features, reacting to the features, reconfiguring. That's the principle. Now we'll see how well that actually works. That sounds good, but we'll see that actually is effective. Question?
AI algorithm on board, it will need some power, right?
Yes. Yeah. But the Jetson, so in terms of flops per watt, these things are amazing, right? That's enabling this too, is that you can run AI on a system that is $1,000, flown in space before, it's TID tolerant, and it's got flops per watt that's better than we ever had before, right? So it's incredible. Yes.
Specifically, what Jetson GPU are you using?
I can get into the details of that. I think this is the Nano, and this is NVIDIA. I can give you the details. It'll come to me. I can't do it right now, but I can.
I'm just curious. I'm familiar enough to look it up, but I don't want to bog you down. But
Yeah, it's one of the Nano. This is this is not the NVIDIA bleeding edge because we picked one that Planet has flown before. So we know it's radiation tolerant, right? But it's not the latest greatest. But it's good enough for us. Okay. Any other questions on that? Yes.
So you talked about the reconfigurable reflecting arrays that has a lot of loss.
Yes.
Due to its reflection. So I heard about meta lenses that are used for millimeter wave wireless focusing. So is that something that
You said lens?
Yes.
Yeah,
lenses.
absolutely. Okay, that's a great idea. Yes, so there are people developing lenses for this application. So those also have their drawbacks. So with a lens, so there's potential for standing waves between the receiver and the lens. So you have to worry about that. It's much harder to enable an electrically scanning system with the lens. So those are the drawbacks for the lens. But there are people developing lenses for millimeter wave. And the other interesting thing, by the way, so I mentioned that the loss of the reflector. So another thing that really helps us there is the Moore's law on silicon, right? So we're going to kind of sit back and let that work itself out. For example, so there's new phase change materials now that work really well for switches up to 200 gigahertz. All right, much lower losses than this. So that's enabling. So there are a number of technologies that we will plug into that, right, to make that much better. Anything else? I think I'm coming to the end here. Am I still on time? I am at the end. Okay, wow. All right. I gave you a whirlwind tour of, TROPICS is kind of a small set, proliferated, affordable constellation for higher visit observations. Very high performance system with a very low price point. We're going to see a lot more of this in the commercial sector. The European government is already doing this, and we'll see how the US responds to that. I showed you performances on par, even better in some cases with much better revisit with this kind of approach. Very excited to see the CREWSR type approaches with better resolution, cognitive sensing that are reacting to the scene, just being smarter about how we make the measurement wholesale. And that's enabled by analysis tools, things that we can do in the laboratory, very high performance silicon processing, both on NVIDIA and for the RFICs, configurable sensors, and we have ways to test that on the ground now and optimize it before we fly it. So very exciting time for kind of new technologies for Earth observation. So happy to answer any more questions if you have any, if we have any time.
I have a quick question on the video. Who is sort of behind that or leading? You said
So I'm the PI on
You're the
VNP.
PI.
Yep, so Colorado State is involved.
Okay.
So on the, what we call the scene generator. So they've got COTS laser projectors used for laser shows.
Okay.
And they've got a system and metamaterials for them.
And that's a NASA funded?
NASA ESTO, yeah, that's
Oh, it's
AIST.
ESTO, okay.
Yep,
All right.
yep. And CREWSR's ESTO as well.
Okay. Yeah.
Okay,